Okay, so welcome to this last session of this conference. So it's a pleasure to introduce Stephen Lynch from King's College, and he is going to talk about mean curvature flow in higher codimensions.
Thank you. Thank you very much, Alessandra and Andrea, for the invitation. It's a real pleasure to have the opportunity to make the pilgrimage to Pisa. The first part of my talk is exactly the same as the start of Peter Topping's talk. We draw some embedded curve in R2. This curve has a curvature vector, which Peter very nicely described as the acceleration of a particle moving at unit speed around the curve. And we can evolve the curve by this curvature vector, giving rise to what's called the curve shortening flow, which is the name given to the mean curvature flow for curves. And it's been known for a long time that if you start with a curve which is embedded, and you evolve it by the curve shortening flow, it will eventually become convex and then continue contracting until it disappears in a point in such a way that parabolic rescalings around this so-called singularity are perfectly round, self-similarly shrinking circles. And this is due to works of Gage Hamilton, and Grayson. That's the situation for embedded curves. And the point I want to make here in this first part of the talk is that if we generalize to immersed curves, then the situation is very different. So if you consider something like a figure 8 with one loop substantially larger than the other, then there's a very conclusive analysis by Angenant of this situation, telling us that as we evolve by the curve shortening flow, the smaller lobe will pinch off in finite time, forming a cusp singularity, and appropriate parabolic rescalings around this singularity will converge to a translating solution of the curve shortening flow, which is probably familiar, the Grim Reaper. Okay. Now, what I want to do is consider, rather than curves lying in the plane R2, a curve which is allowed to bend through three-dimensional space, a space curve. And in this situation, things are far less understood. We still can define a curvature vector in exactly the same way. We can still flow by it in exactly the same way. But our understanding of what singularities form under what initial conditions is far from complete. One of the key reasons is that in this more general setting, even if you start with an embedded curve, it doesn't necessarily need to stay embedded as you evolve it. And it's easy to see this if I draw a sort of curve, which I imagine lying in a horizontal plane with a lot of curvature going to the left, and another curve, which I imagine as lying in a vertical plane with a lot of curvature going to the right. Okay, and then just connect these up in any way you like. This is a nice embedded curve, which if you run it by the curve shortening flow, will very quickly develop a self-intersection. Okay. And this is a key property of these high codimension flows, that there's no preservation of embeddedness, which we can work with to try and understand what's going on. So this tells us that these kinds of cusp singularities where a cusp pinches off in a Grim Reaper are unavoidable, right? In high codimension, even if we start with embedded initial data, the thing can become immersed and form this kind of singularity. One reasonable conjecture might be that for a generic compact initial curve, gamma 0, the curve shortening flow starting from gamma 0 could have self-intersections, right? We've just seen that. But the conjecture might be that generically, eventually, the flow becomes embedded and contracts to a point, becoming round in the process, in the same way as embedded solutions do in the two-dimensional plane. So the conjecture might be that the curve shortening flow eventually becomes embedded and shrinks to a round point. And I wanted to mention some very nice work of Altshuler, where he showed, in general, not only generically, parabolic rescalings of singularities for the curve shortening flow in any codimension always lie in a two-dimensional plane. Okay, so yeah. It's purposely vague. You can make this whatever you like so that the conjecture holds. That's right. Okay, so I mentioned this just to give an indication for some of the issues that come up when we look at high codimension flows as opposed to codimension 1 flows, and to give an impression for the fact that even in apparently the most elementary case of curves, there are still very interesting basic questions which it would be nice to understand. So let me now talk a little bit more about higher dimensions. So in the talk, I'm typically going to be looking at one parameter families of n-dimensional submanifolds of codimension k in a Euclidean space. And such a family is a mean curvature flow if we can parameterize it by a family of immersions, which evolve according to the evolution equation. Df dt is equal to the mean curvature vector. The mean curvature vector being the trace of the second fundamental form. Which now is some vector lying inside a k-dimensional normal space to the submanifold. Okay, so it has freedom to twist around inside the normal bundle. This is a nice weakly parabolic system. We have a nice short-term existence theory. One should think of it as a kind of nonlinear heat equation for submanifolds. And we know that for compact initial data, singularities have to form in finite time. And as we were discussing in the curve case, it's quite interesting to try to work out what these singularities might look like. Here, the story is the same about embeddedness. Even if you start off embedded, this property might not be preserved. And so here again, these kinds of Grim Reaper singularities are an unavoidable part of the theory, which one has to contend with. So this means that a lot of the nice structure of codimension 1 flows which are embedded simply is not available. If you've heard about non-collapsing or multiplicity 1 or curvature gradient estimates, all of these very nice pieces of analytic structure given to you in many settings for embedded flows are simply not available here. And if you haven't heard of those things, maybe it suffices to say that any of the nice topological applications that you've heard of for geometric flows, they probably only work in a setting where you can rule out those kinds of collapsing singularities like the Grim Reaper. Okay, so this is a very interesting new feature when you go to higher codimensions, that these things are, it's not that we don't know whether they're there or not. It's not that if we were smart enough, we could try and rule them out. In general, they are a feature of the theory, which we have to try to learn to work with. That's the first comment. Another comment is that, if you've ever studied the mean curvature flow, one of the first things you do is derive a evolution equation for the second fundamental form. So the first step is to use the first variation formula for the second fundamental form to work out that, and I did it wrong already, the first variation of the second fundamental form is given by the Hessian of the mean curvature plus some cubic reaction term. Okay, so you start here and then use Simon's identity to convert this into a reaction diffusion equation for the second fundamental form. How do you do this? Well, Simon's identity tells you how to commute or to convert the Hessian of the mean curvature into the Laplacian of the second fundamental form. And what you get here is some contraction of the Riemann curvature of the submanifold with the induced metric with the second fundamental form. Plus, since A is now a normal bundle valued form, in this computation, when you compute the covariant derivatives, you pick up a term which is the curvature of the normal bundle. Okay. And by the Gauss and Ricci equations, we can write all of this as some cubic reaction term in the second fundamental form. So I only write this out to give an indication that there's a new player in the game in high codimension. In codimension 1, the curvature of the normal bundle, this R perp, is automatically 0, right? But in higher codimension, it's simply not. And it enters the evolution of the second fundamental form in such a way to complicate the dynamics, right? Sort of induced by these cubic reaction terms. And this is another reason why, well, you can say it two different ways. Either this setting is difficult, or I prefer to say interesting. And maybe one final comment that I'll just say without writing, a sort of effect of this complicated structure of the evolution equations is that there are many more equilibrium states for the flow in some sense. So you may be familiar with this picture that rescalings at singularities often converge to self-similar shrinkers. And conversely, any self-similar shrinker gives you a singularity model for the flow because it shrinks without changing its shape. And if you parabolically rescale it, you get the same thing. So what I want to tell you here is that anytime you have a minimal submanifold of the sphere sitting inside a Euclidean space, it's automatically a higher codimension self-shrinker. Okay, so this means that, I mean, you know, I have to thank my colleagues for constructing so many beautiful minimal submanifolds by min-max and eigenvalue optimization and all of these methods. But every time you do this, you're making my life harder by producing a new singularity model for the mean curvature flow. So every single minimal submanifold of a sphere is every minimal submanifold of a sphere is a singularity model for the high codimension mean curvature flow. That's the punchline. Right. So I've told you a few reasons why this setting is difficult or interesting, depending on your perspective. But yeah, I think for me, the point is that the mean curvature flow is one of the fundamental equations of nature. And so these phenomena are not things to be scared of, but to learn from. So now we move on to the next part of the talk. Why might we be interested in studying this equation? For one thing, it comes up in certain models in mathematical physics, like in the Ginzburg-Landau model. of superconductors. It arises as the evolution equation for vortex filaments. I'm more interested in applications to questions in differential geometry of the kind maybe I've not organized myself well here. So, one of the sort of guiding questions of differential geometry has been which manifolds support geometric structures which are positively curved. And there's been a number of sort of variants of this question that have been successfully addressed using geometric flows. There are applications of this kind of the high codimension mean curvature flow, where by geometric structure, I mean immersion into some Euclidean space. And by positive curvature, well, here we want to impose something involving the second fundamental form. I claim that a very interesting and natural condition is this quadratic inequality, a squared less than or equal to h squared times some constant. So what does this condition mean? Are there any questions while I'm narrating? Yeah. No, there should be heaps of other ones. Yeah, so that's already a bunch, and then there should be loads more. Right. So let's think about this curvature pinching condition, a squared less than or equal to c times h squared on the c-axis. By the Cauchy-Schwarz inequality, c can never be smaller than 1 over n. And if it's equal, then the second fundamental form is umbilic, and the submanifold has to be a round sphere lying inside an affine space. So here, if I have so this is for some Mn lying inside Rn plus K compact. If I have this inequality with C equals 1 over n, then I can only be a round sphere. Of course, by the traced Gauss equations, when C is equal to 1, this condition is just saying that this submanifold has non-negative scalar curvature. And by the Nash embedding theorem, every such manifold can be isometrically embedded into some Euclidean space. So without a restriction on the codimension, determining all the submanifolds that satisfy that pinching condition is as hard as classifying all non-negative scalar curvature manifolds, which is probably tough. And there's a bunch of interesting values in between as well. If we take 1 over n minus 1, in codimension 1, this implies convexity, right? Convexity doesn't make sense anymore in high codimension. But if you like, this quadratic condition with this pinching constant is, in some sense, a high codimension generalization of convexity. So let's put in inverted commas that this is like convexity. And similarly, if you have 1 over n, K is very bad. If you have 1 over n minus m, then this is something like M convexity for the same reason. Okay, so this is another common curvature condition that's studied for hypersurfaces, saying that the sum of any M principal curvatures is non-negative. This quadratic inequality, again, can be thought of as a kind of high codimension generalization of that. Something interesting also happens at 3 over n plus 2. since we're in high codimension, at some point we have to contend with Lagrangian submanifolds, and they appear exactly at this constant. Okay, so there's a classical theorem saying that Lagrangians satisfy this inequality with the opposite direction for C equal to 3 over n plus 2. And there's objects lying exactly at this value, which are called Whitney spheres. So that sort of tells us that if we push C past that value, we're entering into what for me is a strange new world. Okay. So I didn't write anything. This is where we first start to see the appearance of Lagrangians. Okay, but it's not very important for the rest of the talk. I said that this condition is something like convexity, and more evidence for this was given in a beautiful work of Ben Andrews and Charles Baker, where they showed, first of all, that in every dimension and codimension, the inequality, so our pinching inequality with constant 4 over 3n is preserved by the high codimension mean curvature flow. And in particular, this tells us that the quadratic analog of M convexity is preserved as long as the dimension is large enough. So we have that quadratic M convexity is preserved if the dimension is bigger or equal than 4m. And in the case where n is at least 4, and you take as your pinching constant this value 1 over n minus 1, they can say much more about the behavior of the flow. So if on our initial submanifold we satisfy 1 over n minus 1 pinching, then the mean curvature flow starting from this initial value contracts to a point and asymptotically, in the sense of parabolic rescalings, converges to a round sphere inside which is codimension 1 inside some affine subspace of the ambient. So let me just say becoming round. And this, of course, is a beautiful high codimension generalization of the seminal paper of Gerhard-Hüsken on contraction of convex hypersurfaces by the mean curvature flow. And has the nice topological conclusion that the initial submanifold is actually the boundary of an immersed disk. Okay, so there's a very strong topological conclusion that we get from this classification of singularities. Right, but this is sort of in the convex case, and it's very natural to try and push the analysis further and try and understand what happens if we weaken this to K convex, or, in this range of pinching constants where the pinching is actually preserved by the Andrews-Baker theorem. So I want to talk to you about a lot of progress on this question that's been achieved in the last 5 years or so. Any quick questions? Or not quick ones? To be generic, no idea. So even for surfaces in R4, it seems to be a very hard problem to work out which shrinkers are dynamically stable, which would be the first step to doing this kind of genericity result. So there's been some progress on this by Cody Minicosi, but that's a very important problem. If anyone's looking for something to do, work out which shrinkers are stable in high codimension. All right. I want to tell you a bit about what this flow is doing if we increase the pinching constant so that so that this analysis of Andrews-Baker in the quadratically convex case doesn't necessarily apply. So let's take an initial submanifold satisfying our pinching condition to begin with, just with the largest constant allowed by the Andrews-Baker theorem, right, which is actually preserved by the flow. And let's take the dimension to be at least 8. So there are things we can say in smaller dimensions, but they're not as clean. Okay, if we make this restriction, then the discussion will be much more straightforward. Right. Then we now know a lot about what the singularity is, at least their broad analytical structure, what it has to be in this setting. There was a paper by Hui Nguyen where he established curvature gradient estimates in this setting. So his work tells us that at every point on MT, for all times up to the first singular time, which I denote by capital T, we have this scaling invariant gradient estimate for the second fundamental form, where the constant C only depends on the dimension and the initial datum, which of course, goes back to the gradient estimate of Huskin and Carlos Sinistrari in their work on two convex hypersurface flows. This is an extremely powerful tool for studying singularities, principally because it lets you actually take limits of parabolic rescalings in a smooth way. And this Hui was able to prove only using the maximum principle. This is an extremely powerful tool. Next, Keaton Naff, in his PhD at Columbia, proved an amazing estimate, telling us that as the curvature blows up, as we approach a singularity, the geometry is becoming codimension 1 inside some affine subspace. So to state his estimate, I need to mention that under this pinching condition, the mean curvature vector doesn't vanish. So I can always define a unit normal inside the normal bundle just by normalizing H. And this gives me a nice decomposition of the second fundamental form into a part which is parallel to nu, right? So parallel to the mean curvature direction, and a part which is orthogonal. And if you're a hypersurface, this orthogonal part is automatically 0. It turns out that under this quadratic pinching condition, that's if and only if. Okay, so if I have a submanifold where the orthogonal part A minus is 0, then it actually has to be a hypersurface inside some affine subspace inside the ambient. And Keaton's estimate tells you that if you take this, if you like, high codimension part of the second fundamental form and look at the squared norm, this is bounded by a constant times h to the 2 minus sigma. Okay, so the scaling invariant estimate would be without the sigma. This is better by a power, where C only depends on n in the initial datum, and same for sigma. Right, so what this is telling you is that as you approach a singularity, as the curvature blows up, relative to the size of the full second fundamental form, this orthogonal part A minus is going to 0. And this again is proven only using the maximum principle with a very delicate estimation of terms. So it's really very impressive. So what next? Together with Nguyen, we were able to go a step further and say that, right, so now we know that in some sense, as we approach a singularity, this part A minus is becoming negligible. What we showed is that the negative part of little h, the sort of principal component of the second fundamental form, is also becoming negligible. So this is a kind of convexity estimate telling you that not only is the second fundamental form sort of pinching onto something codimension 1, it's also pinching onto something positive, right? Forcing convexity of the submanifold as you approach the singularity. So our estimate says that if you take the smallest eigenvalue of the principal part of the second fundamental form, which I can write in this way, and so this is, for all positive epsilon. If I add on epsilon times the mean curvature, then this is bounded from below by a constant times h to the 1 minus sigma. Okay, where again, the scale invariant estimate would be without the sigma. This is better by a power and tells you that as h blows up, if I divide through by h to make the left-hand side scale invariant, this quantity is becoming non-negative. Okay, so the negative part of h is being diffused away in high curvature regions. So this is where, again, C only depends on n and m0, and sigma only depends on n and m0. And I can say 2 words about the proof of this. So we cook up this quantity, which first is minus the thing that we want to estimate. Then it turns out to be useful to add in a huge constant times a minus squared over h. And then we divide through by essentially the pinching quantity to the 1 minus sigma over 2. Okay, and the proof then proceeds by establishing a global uniform soup estimate for this function via, let me say, using the fact that if you hit it with the heat operator, it has this form, let's say some small delta prime f. We have a good gradient term and a bunch of further terms, which in the analysis turn out to be lower order. And anyone who's sort of studied the proofs of these pinching estimates for the mean curvature flow recognizes this structure. The 0th order reaction terms are not good enough to give us any sort of improvement of the second fundamental form. And indeed, we have this slightly unfavorable term here. Slightly unfavorable reaction term. On the other hand, we have this good quadratic gradient term. These two things can't compete with each other point-wise, so you can't use the maximum principle. But it's possible to exploit this structure in an iteration scheme using Poincare and Sobolev inequalities. So this soup estimate comes from the iteration of, in the mean curvature flow literature, this is usually called Stampacchia iteration, but maybe because of the occasion, I'll refer to it possibly properly as the De Giorgi iteration, which of course was brought into the study of mean curvature flow in this kind of way by Huisken. So that's the game, to cook up a quantity to which we can implement this iteration scheme to get a super estimate. Maybe the only creative thing here is to bring in this funny codimension term, a minus squared over h. This is lower order by NAF's so-called planarity estimate, but by introducing it, we get a good Bochner term, which we can use to control various terms in the evolution of the smallest eigenvalue of h, which are influenced by the torsion of the principal normal vector. Okay, so when you compute the evolution of h, it's a projected onto nu, so you have to take derivatives of nu, which are going to give you torsion terms. And the way that it turns out you can control these is by introducing this extra term and then exploiting NAF's estimate to, show that this is of sufficiently low order that it doesn't mess up the iteration scheme. Right, that's the convexity estimate, which of course I should say is what this is inspired by and similar to the convexity estimate for mean convex mean curvature flow of hypersurfaces, again due to Huisken and Sinistrari, with very similar results proven by Brian White at the same time. Good. So from all of this, what do we conclude? Does anyone else want to say something? Okay. What we conclude from all of this is that in this setting, okay, so for compact initial data, dimension at least 8, with this pinching condition, we can say a lot about any parabolic rescaling of a singularity. So if I say let MT hat, which is going to be an ancient solution, be a parabolic blow-up limit of MT, then as a consequence of the estimates that I've just showed you, we know that a minus squared has to be vanishing everywhere, which implies that MT is a hypersurface inside of some Rn plus 1, inside of Rn plus k. We know by the convexity estimate that the principal part of the second fundamental form is non-negative, and this allows one to conclude that each of these hypersurfaces, MT, is actually the boundary of a convex body. And there's one more point that I want to put here. But first I have to mention another theorem, which I proved together with Theodora Bourny, Matt Langford, nobody else. We showed that so for an ancient solution satisfying these conditions, namely, well, for an ancient solution which is convex, and in addition, satisfies a sort of scalar curvature pinching condition. So let's say this is 1 minus some a squared is less than or equal to 1 minus alpha h squared for some positive alpha, right? Which is clearly implied by our stronger 4 over 3n pinching. For any convex ancient solution of mean curvature flow with this condition, we conclude that the solution has to be non-collapsing. So here there's a word missing. Every convex ancient solution with scalar curvature pinching is non-collapsing. Okay, which just means that if you draw your convex body, take some point X, then you always have an inscribed ball whose radius is bigger than or equal to a uniform constant times 1 over h at x. So this is a kind of quantitative embeddedness telling you that curvature control implies volume control of the enclosed region. So from this, we conclude that blow-ups of this high codimension flow are also non-collapsing. Okay, in particular, you can't see something like this Grim Reaper that we discussed in the beginning. So this is kind of curious if you compare with the discussion of, that we had at the beginning saying that in high codimensions, we can't preserve embeddedness. And so what this is telling you is that under this pinching condition, for the same reason, you cannot expect embeddedness. But as you approach a singularity, somehow any self-intersections are being pushed so far out in space that after parabolically blowing up, you don't see them anymore. And what you get is not only something convex in codimension 1, but it's even quantitatively embedded in this very strong sense of non-collapsing. And a story that's been unfolding over the last, say, 10 years or so is that this class of ancient solutions, convex and non-collapsing, it now seems likely that it's possible to completely classify them, possibly in all dimensions. This has been done sort of in the uniformly two convex case by Brendler and Choi. And there's been a whole bunch of recent work on the three convex case as well. So what I want to say is just that if you drop either the convexity or the non-collapsing, there's probably no hope of classifying this class of ancient solutions. But with these two conditions, there is. Okay, so this corollary with all of the parts put together indicates that it should be possible to classify all of these singularity models. Yeah. It's one. Yeah, so I could have said that. I guess first you get it for some constant, and then you can argue that actually it has to be one. Yeah. Um, well, in the last few seconds, maybe let me mention one piece of ongoing work, which ought to be complete pretty soon. So we had this discussion of the different pinching constants and how pinching with constant 1 over n minus 2 should be something like a high codimension analog of 2 convexity. So let's impose this on our initial data for n at least 8. And so this is preserved. And given that there's a mean curvature flow with surgeries for 2 convex hypersurfaces due to Huisken and Sinistrari, one might dream that there could be a similar object here. And so we can confirm this with Hui. The statement is that there then exists MT, a mean curvature flow with surgeries starting from M0. Which, so this flow terminates after finitely many surgeries. And all of the surgeries are sufficiently nicely controlled analytically and topologically so that we get a complete classification of which possible topologies are allowed for the initial datum M0. So this flow with surgeries exhibits M0 as being diffeomorphic either to Sn or to a connected sum of S1 cross Sn minus 1s. The hope somehow was that with all of these estimates, we had enough control already to do the surgery. This turned out not to be the case. You actually require much, much stronger estimates on these high curvature regions to be able to do surgery in such a way as to maintain the, the constants in all of the key a priori estimates. So this has turned into a bit of a long story, which, well, I'll be very pleased to talk to you about in a future talk. I think I can stop here.
Oh,
Thanks for the beautiful talk. So you mentioned this minimal surface, what Carla also asked about. This somehow reminded me that of this technique of projecting higher core-dimensional flows to particular submanifolds whenever such a projection exists in the diffeomorphic way. This was like applied to, for example, mean curvature flows in Lorentzian manifolds. Have you heard about such technique for this case as well? So basically forgetting particular directions of the flow by projecting it to submanifolds and running mean curvature flow in these submanifolds.
Yeah, to be honest, I'm not familiar with this idea. So yeah, I'd be very happy to hear more about it from you, but it's not something that I know about.
All right, thanks.
Since we have time, can you give us at least an inkling of the extra estimate you need for the surgery?
Yes. So there's a few of them. It turns out that I'll tell you at least some of them, at least a little bit. So the surgery is done on regions of the submanifold which look like necks. And there's a technique first implemented in the hypersurface case by Huisken and Sinistrari for bending the neck inwards by a convex function so that you can cut it and cap it off in such a way as to maintain all of the a priori estimates. But understanding how the geometry changes when you do this bending is already delicate in the hypersurface case and becomes genuinely pretty difficult in the high codimension case. In particular, you get error terms which involve gradients of the sort of secondary part of the second fundamental form. And what you would like to do, even to get things started, is to say that these are much, much smaller than the components in the principal direction nu. And if you look at Naf's estimate, he tells you that A minus squared is of lower order, but this doesn't immediately tell you something about gradients of A minus. So the first thing that we needed to do was to prove some estimates which let you, conclude from the fact that A minus is lower order, that derivatives of A minus are also of lower order. So the way that we've done this is to prove sort of analogs of your interior estimates with class Ecker, but only involving these A minus components. So the estimate would be sort of the form, the soup over a parabolic cylinder of grad A minus squared is bounded by a constant times A minus to the 4. Okay. And so this lets you, on your neck, you can sort of kick things off by saying, since I know that A minus is of lower order with respect to the mean curvature, and I always have, some parabolic neighborhood where I can use this estimate, then I get that gradients are also of lower order. So this at least tells you that when you do the bending, you have some hope of dealing with these new error terms. Because, I mean, in Keaton's estimate, sorry if I'm talking too long, I'll finish now. In Keaton's estimate, this is what we need to preserve, right? With the same constant C and the same constant sigma. This is what's preserved by the maximum principle. This is a disaster because it's not scaling invariant. So we want to make our necks smaller and smaller and smaller so that all the, geometric information in the other estimates is more powerful. But then we have this h to the sigma floating around here, which is blowing up. So, to do this bending with errors small enough such that we can still preserve this estimate, which is not scale invariant, is very delicate. And this is one of the first key ingredients, but there are also more.
More comments? If not, let's thank the speaker again. Okay, let's continue. Now we have Lang Huang from University of Connecticut, and she will talk us about the causal character of Killing vectors and geometry of ADM mass minimizer.
Thanks, Esther, for the introduction. And I really want to thank the organizers, Alessandro and Andrea, for organizing such a wonderful conference. And it's really my honor to speak here. So I will talk about causal character of Killing vectors and geometry of ADM mass minimizers. So one of the best things to speak on last day is I don't really need to define much. So we heard about positive mass theorem. Most of the conference talk about the Riemannian version. So there is a general version, sometimes called the space-time positive mass theorem. It's for the initial data set of n-dimensional manifold with a Riemannian matrix and a symmetric 0 to tensor. And it's called asymptotic flat and satisfy the dominant energy condition. And so here we assume the dimension n is between 3 or 7, or the manifold is spin, a topological condition. Then the conclusion is the energy is greater or equal to the length of the linear momentum. So you heard about the energy, which is in the Riemannian case exactly the same formula as the mass. And the linear momentum is a constant vector of this initial data set defined using K. And here, the general positive mass theorem says this as a n+1 vector, the Lorentzian length has this relation. Okay. So of course, the positive mass theorem has a really long history. For the Riemannian case, you heard about a lot of beautiful results. For the initial data set case, so I think the first result is for Shen Yao. Use John's graph to reduce to the Riemannian case, and that's later generalized by Eckemeier. And what that John's graph approach can show is E greater or equal to 0. So it's also called the positive energy theorem. And then there's a Wheaton's proof, which handle the fold inequality and assume manifold spin. And much later, like about 10 years ago, with Eckemeier, then Lee and Rick Shen we extend the minimal surface approach in the Riemannian case to this setting using MATS, marginally altered trap surfaces. And thus prove the full inequality with the dimensional restriction. Okay. And we also, in the same paper, we have a second proof to prove some density theorems to say we can approximate, suppose the equality fails, then we can approximate by something with exactly vacuum. And you can also use the boost result for Chris Todulu Omohara to reduce this case to the positive energy theorem. So there are two proofs in this general inequality. And there's a recent very nice approach by level set method by Hirsch, Sven Hirsch, Kazaras, and Curie. They use the level set methods originated from Daniel Stern, and thus prove the space-time positive mass theory in the three-dimensional case. Okay. So what I'm interested in today is the equality case. So the conjectured equality case is the following, right? So unlike like a Riemannian case, we really want to show the Riemannian manifold is flat itself, right? But in the space-time setting, you are thinking about this is coming from old slides in the space-time. So you don't expect to say this initial data set is flat in any intrinsic sense. So what's conjecture is like the space-time correspond to it must be like the one with zero mass, and the conjecture has to be Minkowski. Embeds in Minkowski in the sense this is isometric embedding into this Minkowski and with the induced second fundamental form K. Right, so it's really a valid slice in Minkowski. So there, so this exactly result is not proven in all of this previous work. Even in Wheaton's proof, it's direct proof, but he didn't give a complete argument for the case equality. You can only get when E equal to 0. So there are a lot of partial results. And the first complete proof for the spin case was given by Beck, Kushel. And it's written in 3 dimensions and later in journal dimension spin case. By Kushel Martin. So this is spin. And then for much later, greatly inspired by their work, so Dan Lee and I, we proved a general case without spin assumption. Oh, so but the following statement. So this conjecture is true if, again, the dimension of the initial data set is true if either n is equal to 3 or 4, or in higher dimension, we need to impose the added, so some extra asymptotic fall-off rate stronger than the one we need to assume for the positivity. With decay assumption. For quite a long time, we thought this complete, just the techniques are not sharp enough until later by working on a different bi-related project, we realized actually there are counterexamples for this conjectured statement. So of course, physics is only conjecture for 3+1 dimension, right? But then there are actually counterexamples in higher dimension for the equality case. From PP waves. So I will go into define PP waves. So that's, we first wrote down the examples in dimension greater than 5. Sorry, I also forgot to mention for the this one, there is a level set approach is also quite direct. And there's an equality case by Sven Hirsch and Yiyuan Zhang for this 3-dimensional case. Okay, so then they later improved our analysis in the PP waves construction. They can construct up to dimension greater or equal to 5. So in other sense, I think this statement is sharp. If you don't not assume these extra decay assumptions, then they are non-Minkowski space-time, such that you can find the slides with energy and momentum are not zero, but they're equal. Okay. So what are PP waves? So the PP waves are a spatial type of space-time. So I'm going to denote n to be the n+1 manifold. And if I'm doing consistently, the bar is going to denote the space-time quantity. So this is the Lorentzian matrix. So this space-time is a PP wave. If first it has a Killing vector field, and the Killing vector field is actually stronger is parallel node vector field. Parallel or covariantly constant null vector field. Okay, and then moreover, you can looking at the integral hypersurface of the perpendicular vector space to y, and the integral surface has induced a flat matrix. Has induced flat matrix. So the integral hypersurface is actually a null hypersurface, right? Because it's perpendicular to a null vector. Induced, but then we require the induced matrix to be flat. So for this type of matrix, you can actually write down local coordinates. So think about, for simplicity, let's assume it's just a matrix defined on Rn+1. And then the G bar can be write down in coordinates to be, I think it's 2D, UDZ, and some function z squared, and then plus the x1 squared plus. So it's complete written down, and the only reason you get is the scalar function defined on these coordinates. So first you can see partial u does not appear in this, the partial u, the u squared does not appear, right? So it's going to be a null vector. And then since the coefficients are independent of u, so this is a covariantly, is a parallel null vector. Okay, and in the case S equals 1 identically, this is just another way to write down the matrix. So in the case of S equal to 1, it's Minkowski in the different coordinates. So now if we draw the usual t coordinates in Minkowski, so this is say x1. And then you have a lot of this parallel null vector, right? So for example, you can take dt minus ddx1. And then what's the integral hypersurface to it? It's actually the one point in this direction, right? Because if it's perpendicular to null, but it's actually null vector, so the null vector lies along the integral surface. And now if I extend into a higher dimensional case, you should think about that's like a flat plane cut the board at this line, right? So it's going to be, this is the y perp in the general dimension. And then being flat, the induced, so this hypersurface is no hypersurface, has the flat induced matrix. You can think about if I take a space-like slice inside, it's going to be flat. So physicists give the name PP wave because it indicates it's plane fronted. You have this wave front which travel in the parallel ray direction. Fronted for the first P, and the second P is the parallel ray. Indicate the constant, the parallel null vector. But the upshot of this matrix is you can have a lot of choices for S, right? Not particular S equals 1. So in fact, physicists has been studying this kind of PP waves for a really, really long time. But in fact, this is actually first found by mathematician. So it's in 1925 by Brickman. So Brickman studied a complete, like a different reasons, essentially nothing to do with physics, is he want to study the Ricci flat space-time, which can conformal to another Ricci flat space-time. So he find the condition of the conformal factor, and then it turns out he can find this family of matrix. Okay. He actually found more general though. So he find all this space-time which has the parallel null vector. So in some literature, it's usually also called the Brickman space-time if it has parallel. Being PP wave means you have extra some condition on the the plane fronted, the induced flat matrix. So this is exactly 100 years ago. So the celebration of PP wave, and this is actually comes from his thesis, and his advisor is the famous Birkhoff theorem. So there's definitely a tradition there. So I told you this has been studied by physicists for a long time because it's actually a mathematical model for gravitation wave, because the gravitation wave travel in the null direction, right? But what's interesting is in the low dimensional case, you can never make this asymptotic flat with the dominant energy condition. So if you assume dominant energy condition, then in n equal to 3 and 4, by the dominant energy condition is equivalent to saying this function in n minus 1 dimension is a superharmonic function. But then in the case n equal to 3, there is no bounded superharmonic function on R2, right? So there's an example, but similar argument you can say in n dimension equal to 4, there's also no such superharmonic function. And what we really find out is you can make the space-time asymptotic flat in higher dimension and make it complete, define everywhere on Rn plus 1 and satisfy the dominant energy condition. So that's what those examples are about. Okay. So now we have this beautiful conjecture, which somehow should be physically reasonable, right? Because the mass should be model how much gravitational mass contained in the system. And if it has no mass, it should be Minkowski. But now we have these strange PP wave examples. But what's very interesting, recent result, by Sven Hirsch and Yuan Zhang, they show in fact, the PP waves are the only counterexamples. In the sense, actually, if equality holds, then the initial data set must embed in the PP wave. But notice the PP wave is a gigantic family of matrix, right? There are a lot of choices of S you can choose from. So they're doing this for spin manifold. For spin manifold. And E equal to P. Then okay. So of course, working on non-spin manifolds, you want to see whether this is true for general initial data set, and that's the first main result. So let's say theorem A. So this is joint work with Sven Hirsch. So we said this is also true without a spin assumption. Okay. That's a very good point. So technically, yes, but also technically not. So what we really do is we treat it as a minimization problem. So whenever you have a positivity holds in any dimension, we don't care about what proof particularly you use. And whenever we know the positivity holds, we can even take spin manifolds, right? But just give a different approach. Whenever you know the positivity of mass holds, and then our argument is purely somehow variational, and we can characterize the minimizer. Thank you. Okay. So what's the rough idea in the case of spin is you have the spinner, Dirac spinner from the beautiful Witten's equation, and you look in the identity. In the case of zero mass, by the way, so this is defined to be, sorry, this length. And so if this equal to zero, we call it the zero ADM mass. And then in the case of spin, you have the spinner from the Witten's identity, and then you're looking at like everything equals. So that gives the identity for the Dirac spinner. And then interestingly, the spinner already come up a vector field. You can just take the length, take some combination, and then you give you a vector field, and that vector field is parallel null. So the only thing you need to do is to get extra from the spinner equation to show the integral hypersurface of the perpendicular part is flat. And in contrast, without the spin assumption, what result prior to this is we only had, again, a Killing vector field, but the big problem is we have no idea about the causality of the Killing vector. So roughly speaking, is a spinner method give you the zero order information of the Killing vector field. But then this roughly give you the derivative order information. So you don't really know the causality. And so the proof is more involved than the spinner proof. But actually, the arguments can prove something even more, which I don't think there's any spinner proof yet. So that's related to the Barnick quasi-local mass, or in Geha's talk mentioned the Barnick capacity. So Barnick has this really great idea. To define, how do you define the mass of a compact region with boundary? So let omega G0, K0 be a compact initial data set. Right? So then I think he proposed this around 1989. That was like a all the positive mass theorems were just proved by mathematicians, right? And I think naturally he want to relate this to the positive mass theorem. So he considered this instead as a compact manifold. He wants to put it in a big asymptotic flat initial data set where you can define ADM mass. But of course, you have a lot of choices of the asymptotic flat initial data set you can put into omega. So then you can also create the lot of like a black holes in the extension to make the mass arbitrarily large, right? So what he proposed is to take, so he defined the Barnick, denote B for Barnick of this compact set to be the infimum of all these ADM mass of extension, which is ADM means this way, energy minus the length, where this is a so-called admissible family. So what do we mean admissible? So I will use a slightly different formulation as Gerhard's talk. So what Gerhard uses like a very original definition of Barnick, but later Barnick himself also evolved a slightly different definition. So I'm going to treat, this is my compact set with boundary, right? So this is boundary of omega. This is omega, possible with a lot of topology inside. And I'm going to consider M just to be the exterior. So instead of thinking about M is like the whole space where omega immersed or embedded inside, I really just treat M as the exterior. So being admissible means the boundary of M diffeomorphic, or you can glue this to the compact set, and then it has matching Barnick boundary condition. So you have a matrix G, and the symmetric tensor K outside, and you have G0, K0 inside. So you want somehow matching along the boundary. So we look at the induced matrix. So T denote in my notation is the tangential part. And then we want the mean curvature match from inside and from the matrix inside and from matrix outside. And then we also want some matching condition for K. So it's K nu. Right, so the K is a two tensor, right? So if we restrict over the unit node vector, and then the tangential part has to match. And also the trace has to match. So it's not really, we're not really using this boundary condition in the talk explicitly, but roughly it says this condition, he shows guarantee the dominant energy condition, although may not be smooth across the corner, it actually it holds distributionally. Okay, and then there's also another like a no horizon condition. So, and then either you can assume N does not contain, has no horizon, homologous to the boundary, or you can also assume by later, like the formulation by Hilbray and by Gerhard, say it's the boundary is our minimizing. Also, it's not terribly relevant for the thing I'm going to say later, because the condition we need is really just need the open condition. We do the perturbation. So we just need this condition persist after you perturb the initial data set on N. Okay. So this condition is to rule out, for example, you don't want to have you stuck in a very small black hole inside, or they say the bag of gold inside becomes really heavy and produce a lot of mass. So you won't prevent this to happen. Okay. So naturally, there are a lot of questions after this notion was proposed. So first, of course, the question is, do you have such extension? So it has been pretty successfully constructed. You can, in fact, construct extensions. So you are, in many cases, so you are minimizing this amount of non-empty set. And then the second question is, does the infimum, is the infimum realized? Right, so that's a question about so-called Barnick mass minimizer. So the Barnick mass minimizer is the extension such that the ADM mass reached the infimum. Okay. So the question is, does a minimizer exist? It turns out to be an extremely hard question. So I'm not aware of anything about existence, but there are a lot of examples of non-existence. So you can construct a compact set with some boundary condition, and then you show it actually the mass is not infima. The infima is not realized by some extension. But then also, another question is, if a minimizer exists, what kind of property does it have? So it's usually called a Barnick stationary vacuum conjecture. So that's first, when you propose this, he asked, he conjectured this following statement. So a Barnick mass minimizer so let's say N, G, K, the exterior, the asymptotic flat end of some compact set. If it's realized, if it exists, then it has to be a vacuum and stationary. So the stationary in this setting means so you have a Killing vector field of the space-time, and then the space-time, the Killing vector field is time-like, near infinity. So being time-like just means somehow it points in the time direction, or equivalently, the Lorentzian length is negative. So for the stationary vacuum case, I think relatively little was known. So there was a result for a three-dimensional case by Zhongshan and for n equal to 3 and assuming vacuum. So vacuum, remember, is part of the conclusion, right? But once you assume that, then she can show the existence of this Killing vector. And then there's also some partial progress me with Dan Lee. I will talk about this result a little bit. So partial progress. So we cannot really show the space-time where NGKC inside has this nice property. But we can show you at least there is some such space-time with some property. So the physical intuition of this conjecture is, if it's mass minimizer, that means the extension should not have matter field, right? So then it's vacuum, because somehow the matter field probably give you more mass. So it should be vacuum. And then if it's mass minimizer, it should be like has no gravitational dynamics, right? Then that means it has to be stationary. So that's what the physical intuition is written in the paper, in that paper. But it turns out it may be good to have little physical intuition sometimes as I do, because there are counterexamples to the zero Barnick mass case, which exactly is coming from the PP wave. So when the case right, so there are PP wave counterexample. So again, we only know the example in great dimension greater than or equal to 5. And that follows from the analysis here leads us to find out the PP waves. But to give fair credits to Barnick, he only conjectured the case for n equal to 3, right? But just the formulation can be generalized in any dimension. Okay. And there's also the Riemannian case, right? We love Riemannian case. So what happened in the Riemannian case? So it's usually called the static vacuum conjecture. It's more or less well known by now. So if you're just looking at your compact set has no k is 0, and then you do extension over the manifold which k is 0, so then you get the Barnick mass minimizer is static in the sense there exists a function right? But moreover, there's like a stationary part, right? You want to show so this corresponds to the lapse of the Killing vector. So that's the Killing vector is in the no direction, the length of the Killing vector. So you want to show the length is, so f is positive and f goes to 1 near infinity. Okay, so this is really related to the scalar curvature deformation problems. So being static has been shown by Justin Covino. And then the asymptotics and the positivity was shown by Anderson Jergy. Or they need to assume a slightly stronger assumption on the minimizing admissible family. So assuming minimizing a larger admissible family. So they need to assume you're looking at admissible extension can allow the mean curvature to be less or equal, not exactly equal. Okay. So let me write here. So the theorem B we have is more or less the same approach for this equality case. We can prove the stationary conjecture. But you tell me like there are counterexamples, right? I know what you're thinking in your head. So the case we can show is when the case of Barnick mass is positive. So positive. So the counterexamples are in dimension greater or equal to 5 and the case of 0 Barnick mass. Then we can show the space-time so it embeds in the space-time that is vacuum, stationary, and we also show a little bit stronger than what's proposed there. And in fact, the vector field is uniformly stationary, uniformly and strongly. strongly means it actually is time-like everywhere, including the interior. And uniformly means the length actually has a negative upper bound. So you will not asymptotically know. Okay. All right. And our argument also extend the static case by removing that assumption. So it's a minor improvement in the static case. So I'm going to use the rest of time to talk about arguments. So even the setting may be foreign to you if you haven't worked on this initial data set stuff, but I hope you feel the techniques are greatly inspired by a lot of things in geometry analysis. So before I proceed, any questions? Okay. Okay, so by prior results, we already know. So for example, by the ingredients already there, by Barnick's Lagrange massive Lagrange multiplier. So in fact, this is treated as a constraint minimization problem, right? So there is a functional you can work such that this mass minimizer is the minimum of that functional, but among constraint, the constraint is the dominant energy condition, right? Or in the Riemannian case, it's non-negative scale curvature. So then you are minimizing among constraint, and then Barnick has this wonderful idea to introduce the massive Lagrange multiplier for Banach manifolds in this setting. And together with, in the paper with Denley, we developed the deformation theory for the dominant energy condition. So together, what we can already show, so if it's a mass minimizer in either theorem A or theorem B case, it has to embed in a space-time using the Killing development of bicrucial, where it admits a Killing vector field. So being has a Killing vector field is something quite special, right? Because that means the space-time has symmetry. So why? And moreover, we know what's the Einstein equation for G bar. So G bar is actually so-called the no dust, which is just a fancy name to say the Ricci of the matrix has some structure. So it has to proportion to the velocity given by the Killing vector field. And here alpha is a scalar. It's a proportion scalar function. And so we know very specific what alpha is, but just for the talk, alpha is, if alpha is 0, then it's vacuum, right? If alpha is not 0, we actually know the Killing vector field has to be null. Okay, so that's how it leads us to, find out this as in the PP waves, right? Because we're looking for space-time has this structure. And this in physics literature called no dust. It's really the model of the massless no dust travel in the direction of y. And in this case, it could be a null if it's not vacuum. So let's know before. So what's the new thing? So the new ingredients, the first one is we get this Killing vector field, right? But we have no knowledge about the causality. Remember, in the first theorem, we want to show is PP wave, so we want to show y is at least null, even better, parallel. In the second case, we want to show is time-like, right? So then we first want to rule out the case is being so-called space-like. So we want to rule out that case. So first we will show why is the terminology is causal. Causal means either null or time-like. And so I probably will talk about the second part, the second ingredients, because I find the second ingredient is probably more interesting. But just tell me this. So this just let you know what this being done. So it's really using the variational feature. So then once you have constraint minimization, you can redefine the functional to make it critical point of some functional exactly, not the constraint, right? So in the calculus case, you probably have the constraint f x0 equal to the Lagrange multiplier times your constraint, and then you just redefine your functional to be at least one, and then the lambda, and then x0 is going to be a critical point of this new functional. So we actually know it's a critical point of a new functional, and then we find out if the vector field is time-like somewhere, we can construct perturb initial data set of this guy, and then to make dominant edge condition holds, and then the mass will go down. So they contradict mass minimizing property. So let me just say by variational approach of so-called rigid Heidelberg functional. Okay. And the second part is something I think is probably you can just take completely irrelevant to what I have been talking about is in general, if a space-time has a Killing vector field, and now you know it's causal, what can you say about its causality? So the setting is now we have a space-time, and then we'll assume it satisfies some condition, energy condition. The condition we need, so here we assume we have a y is a causal Killing vector field, and then you assume the space-time matrix has this energy condition, which is reaching along the Killing vector direction is 0. So this I think can be relaxed, but let's assume it for now. So of course the minimizer we construct here has that property, right? Because if you plug in y bar, either it's vacuum, so it's 0, or it's null, so it's also 0. And then we have this following property. Also, we take length to be minus of the length, right? So we take minus sign here, so eta is going to be greater equal to 0. Is a function, scalar function on the space-time greater equal to 0 by its causal, by being causal. Okay, so the first theorem we have is there's a strong maxima principle for eta. So on this assumption, so here n doesn't need to be complete. So we really think about n is compact with boundary. There's a compact is a domain in some probably bigger space-time. Then we show the length. So if the minimum of eta is realized at the interior point, then it's actually identically constant. Identically constant. So the particular interest we have is whether the vector field can become a null at the interior point, but time-like elsewhere, right? So this says under this energy condition, it cannot happen. And the second theorem is there's something similar at infinity. So let's call uniform stationary. So here we need asymptotic flatness. So suppose we have a space-time. And then, so let n, gk to be asymptotic flat initial data set in the space-time. And then we assume we have y is killing, is causal killing. Y is, sorry, it's time-like killing. And suppose this, we actually just need to be at exterior, right? So the asymptotic flat initial data set doesn't need to be complete. We just care about the behavior at end. So then we also have this Ricci condition. And then the conclusion is the y has to be asymptotic, has to be uniformly asymptotic in the sense eta, which is a negative length, has to be greater than epsilon for some constant epsilon. So this is the case when people working on the stationary space-time, they always want to rule out, right? Because if you have a time-like killing vector field, which stay uniform near infinity, and you can use it to construct a space-time coordinates, which the time direction will be the one from the killing vector. But it's not clear whether this uniform stationary will always happen. So in fact, the bicrucial paper, the one they studied the rigidity case, is they can relate this non-uniformity. So if it goes to 0, then it must be the rigidity case of positive mass theorem. So now if you assume global condition where the rigidity tells you must be Minkowski, then you can rule that out. Because for Minkowski, you can you do have other uniformly time-like vector field. So in contrast to bicrucial's result, is our result is purely local. So we only assume condition near infinity. So we find this feature is purely local at infinity. Okay. So since I told you the strong maxima principle, right? So what ingredients you might think about is right, the strong maxima principle in the classical PDE. So we were really inspired by how the Buckner identity being so useful in study killing vector field for Riemannian manifolds. For example, you can show if Riemannian manifold has non-negative Ricci curvature, and every constant length killing vector has to be covariantly constant. So very strong condition. So we want to apply Buckner identity to our Lorentzian matrix. So what we can get is this, the length satisfy some good equation. I think this is 2 times G bar of the gradient Y bar plus the cube of the Ricci. Right, so you will guess like here, that's why we assume the energy condition. So this term will be gone. And in the Riemannian case, it's been really useful identity. The left-hand side is going to a Laplace of the length, and the right-hand side is going to be a term like the norm of the gradient, right? And it's going to be positive. But the thing is, we are in Lorentzian matrix. So this is indefinite. So it does not have obvious positivity. And also, this is no longer Laplace because you do the same thing in the trace of Hessian, you have this one negative direction. It's going to be a wave operator. So for someone who, like me, mostly work on elliptic problems, and you find like very excited because there's tremendous application of wave equations in general relativity, right? And you see, finally, there's a wave equation appear in my research. And then I look up the textbook on wave equation, right, to see any maxima principle, and realize actually there's no maxima principle for wave equation. So close the book. So what we do instead is to slice the operator. So it turns out being a killing, means the length is invariant in Y. So you can slice the equation. So this is on the space-time, but you look at the restriction on the initial data set. And it gives rise a pretty nice equation. So this is, and then, so the restriction on initial data set, then you get this now is a divergence of a Riemannian matrix. I'm going to tell you what F is, sorry, and what X hat is very soon. And then you get a divergence equation, and the right-hand side has a bunch of terms. Oh, so it's a lot of terms. J-I-K-J-K-J-L. Right, so this beautiful equation in the space-time becomes this, okay? But the good thing is, so this, without this extra term, this actually is an elliptic equation. And what's F, right? F is so-called the lapse, and X is so-called the shift. So in other words, for the vector field, Y, you can decompose. So here we have N, and you have a vector field Y, and you can decompose into the normal part and the tangential part. So the normal part, the length is called lapse, it's called N, and then the tangential part is X. So we also decompose the equation Y into the lapse and shift. And this is indeed elliptic in the case if Y is time-like. So X hat is the X divided by F. So if it's time-like, then you know the length of X hat is strictly less than 1, right? So you are subtracting the term which don't destroy your ellipticity. So in fact, the strong maximum principle is a very easy consequence for time-like vector. Then the problem is you want to include the null case is this becomes length 1, and now we are working with a degenerate elliptic PDE. And the degeneracy happens exactly at the null, the points where eta is 0. Degenerate. Okay, and now when looking at those existing literature, they do have some elliptic, they do have strong maxima principle type of thing, like a Hopf lemma for degenerate elliptic PDE. But our equation falls on the worst case, is they are also so-called characteristic points. The characteristic points just means if now I'm looking at this is my N, and this set Z says where eta equal to 0, and the degeneracy exactly at normal direction. And that's really the bad direction. So in fact, they are critical points where you fail to do the maximum principle there. Characteristic point. So what we find out is from this equation, it turns out to have a very beautiful structure on the right-hand side, not written in this current form, but then we use it to derive a monotonicity formula. So if we get sigma t to be the level set of t, and then this following quantity is going to be monotone. I think it's this by half. And for this is monotone, it's decreasing for t greater than 0. And the proof is somehow very similar to the techniques using in the monotonicity of minimal surfaces, right? You integrate and then you use Correa formula to reduce to interior turn to the boundary, and then you get ODE, and then you get monotonicity. In the Riemannian case, it's much simpler. In the Riemannian case, you are working with the x is 0, so you are working with harmonic function, and then this is really just becomes on the level set of f, where this becomes the gradient of f, and this in fact is constant. Okay, so last is how we use this to prove the strong maxima principle, right? For the strong maxima principle, we want to use somehow you can show at where eta is 0. First, you show it's actually a hypersurface. In general, it's just a 0 set. It can be very, very bad. But then you show is at least the boundary of Z is smooth hypersurface. So it'll be remotely related to Professor Minguzzi's talk on the regularity of the Cauchy horizon, right? But here we are in a much simpler case because these are purely local results. Cauchy horizon is a global quantity. But then what we show is if it's at 0, if it's at interior, then you can actually show by some argument, this, although it doesn't define at t equal to 0, it limits to 0. And then it's decreasing, right? So that will imply everywhere is 0. But this is always greater or equal to the norm of gradient eta. So you show gradient eta is 0 everywhere. And the only thing is this is on the level set, right? The whole thing you can apply divergence theorem. So we have to localize this over a region flow out from this smooth part of boundary of zeta. And then you just want to make it, when you flow, the divergence theorem has no boundary turn along this. So we can localize the monotonicity formula. So, and I'll show give a strong maxima principle. Okay, all right, so I'll stop there.
Questions, comments?
Thanks for your nice talk. This uniform stationary property there, how do you prove? Is it similar to like these Array-Joudry arguments where you prove that if you have an infinite null cone, it can't be too curved, for example? Is that a similar argument?
So it's actually using the increasing. So here you are worried about the case infinity is null, right? So you are using this monotonicity from inside. So you can also define this quantity as t goes to 0 toward infinity. And then you find out that quantity has to be 0. And then by decreasing property has to be 0 everywhere where it's defined. So essentially it's the similar idea, but you are looking at local and infinity. Thank you.
Something else?
Thank you for the talk. I have a sort of vague question. You said that this kind of degeneracy for this elliptic PDE is of the worst kind, right? Okay, I was just curious to understand a sort of hierarchy. Is this kind of degeneracy similar to the one of the level set formulation of mean curvature flow or inverse mean curvature flow, or is it worse, roughly speaking?
Let's see. So Sven did tell me like he looked into like the weak level say inverse mean curvature flow, and he told me he finds some familiarity. I could not see it. The reason is I think the degeneracy happened at gradient. The level set has 0 gradient, right? But I think here is regardless of you have 0 gradient or not. So it's really about the degeneracy of for the strong maximal principle is where this somehow there's a bigger reason is because the 0 set correspond to the mods, marginal algebraic surfaces in a space time, and then the vector when you project down, the vector x has to be always normal to this, And then the strong maximum principle, but at least by the whole lemma for the classical proof, you are working with interior sphere condition, right? Somehow you construct barrier really using this function where you have a normal vector of the sphere. And so the argument fails for the characteristic point. I should mention, so I find it really inspiring work, especially where we prove the boundary smooth is by Denson Hill. I think it's the paper in around 60s. So it's probably the starting point of looking at all these like characteristic points of these degenerate elite PDEs.
Okay, thank you. So I'd say it works. It's worse, in fact. I'd say it's worse. This kind of degeneracy.
I don't know. It's worse.
Okay,
it's different.
At least for me. Okay. Thank you.
Right.
Something else?
So probably nonsense, but concerning Barting's quasi-local mass, so if you find, say, an outer space, would it be a flow that decreases the ADM mass?
Let's see. So you are thinking about the flow increase the ADM mass or decrease the ADM mass? Decrease.
Yeah.
Right.
Reach
So let's
a minimaster.
so there's a Ricci flow proof of the positive mass theory in 3 dimensions, right? So then they show I think it's quite the mass is constant along the flow, right? But somehow they can manage to show the positive mass theorem still. And so I think the natural thing for me to guess will be you looking at the Ricci flow with boundary in this case. And that's actually a related question. So I think the Ricci flow with boundary somehow probably it doesn't behave well with this Barnick boundary data. So there is like a conformal boundary data of Anderson, which has been shown you have local existence Ricci flow for manifold with boundary, right? It doesn't handle unbounded manifold. So perhaps I will think about using that kind of Ricci flow, but then you change the Barnick boundary data. So I think there's a static flow by probably Fisher and Qin-Jie. Oh, right, must by Jie Qin, sorry. Jie Qin, I think he told me they propose some kind of static flow to looking at these questions, but I don't know if they can show the long time existence. Probably there's no long time existence result yet, right?
Thanks.
Thanks for the beautiful talk. In the Bartnik mass problem, do you need to assume in 3 dimensions that the trace decays faster?
No, I think we are working with general asymptotics thing because the trace usually is when you're looking at John's graph, right? So here we are not even using positive mass theory or anything. So we are just, I think just a general asymptotics. But assuming it's a mass minimizer. So assuming mass minimizer is already include a lot of condition, right?
Okay.
So somehow you need to, from other reasons to guarantee it's a mass minimizer. But I think it still works as long as you have the positivity of the positive mass theorem.
And for the theorem A, for the PP wave, do you do that just for n bigger than or equal to 5? Or does this argument also, I mean, I know they don't embed because these geodesically complete PP waves don't exist, but do you still do the argument for all dimensions?
That's a good point. I should mention. So this is general holds for any dimensions as long as you know positivity of mass. So even in n dimension 3 or 4, you have this conclusion embedded in PP wave. But then you use PP wave is actually Minkowski in those 2 dimensions. So in other words, that's like a more difficult proof to the equality case. But it doesn't exclude the low dimensional case.
And for that, do you need the trace assumption or also no?
No, there's no trace assumption. Yeah, even in like a spinor proof or something, there's no.
Right. If you use the spinor proof, no. Yeah.
Right. So so the question you may wonder is like case equal to 0, right? If you reduce to once you reduce to equal to 0, then probably you need to use John's equation. So then we now have a small paper we show using this Lagrange multiply method. You can also guarantee it has to be embedded in Minkowski. So it does not assume like a John's equation or anything. Right. Thanks.
Anything else? Then let's thank Lam
Great.
again.
Thank you.
Okay, so let's close the meeting with Mattia Fogagnolo from Padova, and he will talk about isoperimetry and mean convexity.
Perfect. Okay. Thank you very much, Esther. So it's the first time I have to conclude a conference. So before I forget, let me really sincerely thank the organizers, Alessandra and Andrea, for having set up this amazing workshop, this amazing conference. I knew that it was not so easy organizing this whole business here. I think it was really a success. I had a really good time. Talks were amazing. I also happen to know many new people here and also meet known ones. I think I really enjoyed this conference and also talking with people here. I think I'm not the only one who has enjoyed this conference. So thank you very much. And again, before I forget, I think we can all thank the organizers now with a celebrating. Okay. 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 And now I think we can go having lunch. Okay. Okay. So I start with this talk before having lunch. I'll try to be brief, but it's the first time I give this talk. I see many things that could be really wrong, and in particular, that could go wrong, and in particular, I'll struggle to be brief, but I'm not promising it. Okay. So let's start from assuming, and this is a strange assumption, assume we have a mean curvature to be set in a general Riemannian manifolds. There are no assumptions today, sort of, okay? And only assume we have at our disposal a mean curvature in inequality, holding true for any hypersurface, okay? So something like this. For any boundary delta E, we have that a function of the mean curvature is bigger or equal than a function of the perimeter, okay, of E. This for any E in our ambient manifold M, where F and H got really mild assumption. Let's say F H continuous and increasing on 0 infinity. Have in mind some very basic examples like F equal to F of t equal to the modulus of t to some power alpha, or maximum of 0t to the power alpha, and h the very same, some power of t to the power beta, okay? We saw these kind of inequalities appear during these days, okay? Nice thing is that they relate to curvature inequalities, and they usually can be proved, for example, through the various geometric flows we saw on these, also during these days, okay? I'm not talking about how to get this kind of inequalities. We're going to see something that happens when you know you have this kind of inequalities, okay? Because then we make another assumption, that is that we're going to drop in some minutes, okay? That is, we also have isoperimetric sets at our disposal, okay? So assume also that for any positive volume, okay, there exists an isoperimetric set EV, okay, such that the perimeter of EV minimizes the perimeter, okay, among all sets with volume V, okay? Assume also, and the mean curvature of the EV, but this is milder, okay? It's not really needed. It's just for not getting to general functions here, that the mean curvature of this isoperimetric set is positive, okay? Let's also call IV this quantity here, that is in particular is a function of V, okay? very useful, very well studied. It's the isoperimetric profile. Okay, at any given volume V, it gives you the perimeter of the isoperimetric set of volume V. Okay, fine. So why I'm happy with this isoperimetric set? I'm happy because one gets interesting things computing the geometric inequality there, okay, on the isoperimetric set. Why? Because the mean curvature is constant. Okay, so you can take f of h out of the integral. Okay, so we get that the integral of on the isoperimetric set EV of f h, let's call it v, okay, is greater or equal than h of the perimeter of EV, but this is h computed on the isoperimetric profile at volume V. Okay, on the other end, this is constant, okay, so we can take this out, and we get that the isoperimetric profile of V, that's the volume of EV, times f hv, is greater or equal than that quantity there, okay? Moreover, and this is general, okay? Moreover, use that the derivative in a suitable weak sense, okay, of the isoperimetric profile is exactly given by hv. This is substantially the first variation formula, okay? If you compute the derivative of the isoperimetric profile, for the very same reason why the first variation of the area is the mean curvature, you get that first derivative of the isoperimetric profile for the volume V is the mean curvature hv, okay? And you already see here that then this becomes a differential inequality, IV f I prime of V greater or equal than h IV. Okay? Get a differential inequality, and we sometimes know how to integrate differential inequalities. Okay? Particularly in this case, we have that f is invertible, okay, for positive values of the argument. So in particular, you get out of this thing that I prime of V is greater or equal than a suitable function. Let's call it big G, okay, of the isoperimetric profile of V, okay, so that I prime of V over G IV is greater or equal than 1, okay? But then we are in good shape for taking the primitive, okay, the integral of both sides. And what we get is that the isoperimetric profile, okay, let me write it here because I need some space. What we get is that the isoperimetric profile IV is less or equal than some function, okay, of the volume. Okay? Now, what happens? It happens that this is not a random set. It was the isoperimetric set. Okay? So, if we take, let here be any, let f any set contained in M, okay, with volume V, sorry, with volume V, okay? Can you, okay, with volume V. Here you have that this F, okay. Okay, let me call it this big H, okay, no problem. No, it's the mean curvature. Let's call it W. That's the Wilmer function, but it's not so popular now in this talk, okay? So W of V, okay? Then this is also W of computed on the volume of our NEF, okay? And on the other end, sorry, here I have the wrong sign, luckily, okay? Luckily, it's IV greater or equal than, okay? Otherwise, I would have been in big troubles, okay? because the isoperimetric profile now is smaller than the perimeter of F. Okay, because the isoperimetric profile is the perimeter of the isoperimetric set. So it's smaller than the perimeter of F. Okay, so this is smaller than, let's call it this way, okay, the perimeter of F. Okay, and now this holds for any F, because I just took an F of volume V, but we got this inequality for any volume V. We got this isoperimetric inequality for any set F. Okay, so this is how, under these strong assumptions, but I think it's a very useful principle, you get out of a mean curvature inequality an isoperimetric inequality. Okay, there are two very bad assumptions, one in particular, that's somewhere there. Okay, that is, assume we have isoperimetric sets for any volume. Okay, it's not like it's difficult to provide isoperimetric sets. The fact is, usually you don't have isoperimetric sets in a Riemannian manifold. Okay, even if you have sharp isoperimetric inequalities. Okay, some of such manifolds are easy to build. For example, it's quite easy to get manifolds with a negative curvature, also asymptotically flat, without isoperimetric sets at all. But more surprisingly, I think last year, also in the more friendly, usually for this kind of problems, setting of manifolds with positive curvature, okay? It's been constructed manifolds with positive curvature, okay? With Euclidean volume growth, that is, with volumes that grow as those in Rn, okay? I personally expected that in this situation you have isoperimetric sets. It's not the case. You get a threshold such that up to such threshold you don't have isoperimetric sets, and after that threshold you have. But in order to apply this argument, you need to have isoperimetric sets for any volume. Okay, this last example is a result by Gioacchino Antonelli and Federico Claudo. So let me write this one because it's very interesting. In general, no isoperimetric sets. See, for example, Antonelli Claudo. Okay, so you need something more. And now we pass to something more. So I erase. Okay, and we provide a weaker assumption. Okay, we try to weaken this assumption we have on our general manifold. Okay, so assume now that our M, okay, is exhausted, okay, by domains omega I, such that omega I are bounded and the mean curvature of the boundary of omega I is strictly positive. Okay, this is another assumption. For example, we saw sometimes asymptotically flat manifolds. Okay, asymptotically flat manifolds freely come with this kind of exhaustion. Okay, and I just told you that you have asymptotically flat manifolds without isoperimetric sets. So at least in principle, there are two disjoint assumptions. Okay, it's not priori not weaker, not stronger, but for sure you can have this one, but not have isoperimetric sets. Okay, at least. Because what we do now is the following. I forgot to erase it here. Because now we sort of modify this argument by taking EV, say omega, okay, isoperimetric sets among competitors in omega. omega is one of these sets. So such that the perimeter of the omega is the infimum of the perimeter of F, okay, such that F is contained in omega. Okay, this immediately has got an advantage. Isoperimetric sets in a compact domain always exist. Okay, so we don't have this problem anymore, at least. But let us check now whether these kind of arguments of these computations give something or not. Okay. In fact, it turns out. Okay, a picture. So, see, is in the no. Important. Thank you. Not at all. Think of geodesic balls in a asymptotically flat manifold. No, sorry. Very important. Thank you. Otherwise, it would be really crazy assumption. Okay. Okay. So we have our omega, and our supermetric set in general, EV, could be something like this. It can touch the boundary of omega in some region, okay, and have some other region inside our omega. Okay. So this is the boundary of EV intersected the d omega. Okay. This is our EV. This is our omega. Okay. It turns out that the mean curvature here of the EV inside omega, okay. So in this part here, okay, the dV inside the omega is constant, okay. Is constant, is a constant value CV. Okay, let's go on with red, CV. Okay. While the yellow part is a priori only positive, okay? It's not constant, okay? But the important thing, okay, is that now if you just use the minimizing property of EV among all competitors for the perimeter sitting inside omega, okay? In particular, considering variation of these sets in this direction on the red part and in this direction on the yellow part, okay? This gives you another set EVT, okay? Okay? You get that the constant mean curvature here in the red part is bigger, okay? This is really a direct exercise, is bigger than the mean curvature in the tangency part, okay? So only using this kind of variation argument, okay, that employs the fact that this set EV is minimizing the perimeter, you get that this function H the EV inside omega is strictly bigger than the mean curvature of the EV intersected the omega. Okay, that's strictly positive. So we also got for free the second assumption, okay, that was positive mean curvature of the isoperimetric set, okay. But it's not only this. Let's go on with in the other blackboard. Because this monotonicity of the mean curvature is really the key. Because now, moreover, as before, the derivative of the isoperimetric profile, but now it's the isoperimetric profile constrained in omega, okay, is given by the value of the mean curvature in the constant part, okay, in the red part, that's constant, okay? So it's given by the mean curvature, the red mean curvature. That's this one, okay? Okay, so remembering the computations I wrote before, you have that we had this thing, right, f of h, and compute it on the EV omega. F was increasing, okay? So this is less or equal now than f computed on h, okay, on I prime of v omega, v omega. And on the other and on the other side, we still have the same right hand side. Okay. And you see that now this is again constant. Okay. So again, you took it out. So very same computations as before. Times I prime v omega. And you see, we have the very same chain of inequalities, okay, for the constrained isoperimetric profile. Okay, that's the isoperimetric profile for the isoperimetric problem among sets contained in omega that always exist and that also have positive mean curvature if the mean curvature of the exhaustians are positive. Okay, so out of this thing, you get the isoperimetric inequality as before for I use W. So we got d e greater or equal than W of d e for any e now only inside omega, okay? But omega was an exhaustion, okay? So we played this game for any omega in the exhaustion, and we got the isoperimetric profile, the isoperimetric inequality on the whole manifold, okay? But omega I exhaustion. So we can remove this constraint here. What? No, because it always depends on this geometric inequality that I assumed for any domain. Yes, but I'm using the fact that's quite sort of in any non-compact, non-complete manifold that the isoperimetric profile goes to zero as the volume goes to zero. So in fact, you don't really have constant of integrations due to this fact. It's not always like this, and you're going to see an instance where it's not like this, but this is just the general principle, okay? In general, you also get that constants of integration, yeah, for sure. But it's quite often you don't have any, okay? So fine. For sure. When you do the variation. If it's properly inside omega, it's easier. Okay, so I don't know if I understood correctly, but anyway, okay. In general, you get something that can touch the boundary, okay, and it will always touch it tangentially. This is a result, and also the whole boundary is also quite regular. Is C11, okay, okay, here now I'm just using the variation only to here I'm just using the first variation among perturbations, keeping the same volume. Yeah, maybe this was your question. Yeah, here we are keeping the same volume with this perturbation. This is why it's the wrong arrow. This is why, okay, sorry. We are keeping the same volume in the variation. So in fact, we are going inside from above, from the yellow part, and we are recovering the volume on the other one. The arrow is in the wrong direction. Sorry, maybe it's what is puzzling you. We are not really moving inside. We are making a variation with the same volume. So while this kind of variation decreases the volume, you are right. Oh, okay, but anyway, this for sure was a wrong picture. Okay, because the variation had to preserve the volume. I draw something that decreases the volume. Okay, see, yes. Where, sorry? Okay, where? Here it's I. No, 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 no. Okay, fine. So now I have a set of examples where this kind of picture worked properly. Okay, so where we have all of these ingredients. Okay, so let me take it here so that people online can see. Let me reverse it. So these are examples. The very first one, and it's where all of this picture was already very clear. Is the setting of three-dimensional Cartan-Adamard manifolds. Okay, it's the original work of Kleiner of 92. In fact, he succeeded in getting, and this was the key point. This is 16 pi. Okay, in getting a Wilmore inequality. Okay, so a lower bound for the Wilmore functional on a sufficiently broad class of sets. The mean convex exhaustiums came for free from the Hessian comparison because geodesic balls are even convex. Okay, they have positive second fundamental form. Okay, and so coupling the mean curvature inequality with the convex exhaustion, okay, it came up with the sharp isoperimetric inequality in three-dimensional Cartan-Adamard manifolds because this is the sharp constant in Rn for the Wilmore functional. Okay, indeed, all of this picture is as sharp as the curvature inequality is sharp. Okay, so in the very same magnitude. On the Cartan-Adamard manifolds, for those of you who maybe not know, are non-positively curved, okay? The sectional curvature are non-positive, and they are also simply connected, okay? In the positive curvature setting, okay, up to dimension 7, together with Lorenzo Mazzieri, we provided the sharp isoperimetric inequality, okay? With this very same picture, we had a mean curvature inequality in terms of the asymptotic volume ratio that was already introduced in Deborah's talk. And out of this, we got the isoperimetric inequality. Where's the mean convex exhaustion here? Okay, you have two ways to build the mean convex exhaustion in this case. The first one is the one we got sort of by hand, okay? That is minimizing the volume, the perimeter among sets containing a given obstacle, okay? And this gives you an outward minimizing set. Or using more advanced techniques, you can just run the inverse mean curvature flow we saw, for example, in Gerhard's talk, but also in Lucas, okay? Because in this setting, you have an inverse mean curvature flow. It's a result by Kai Xu. So just running it, it gives you an exhaustion of auto-minimizing sets, and in particular, you can get strictly mean convex exhaustions out of that, okay? So these are the ways you provide the mean convex exhaustions in this setting. Then, and this is where constants of integration appear, for example, together with Stefano Borghini, we got an isoperimetric inequality holding true for this class of substatic manifolds. Okay, you have a function u satisfying this inequality here. When you set 0, you get the equation of static manifolds, okay, that already appeared, for example, in Carla's talk, okay? But it's more general. This is a more general situation where you have the inequality. There are examples coming out of general relativity when, in fact, you have strictly positive sign. This function u is 0 at the boundary. So here the novelty is that our manifolds have a boundary. Okay, here in this picture, there are no boundaries for the ambient manifold. In this case, again, we proved a mean curvature inequality for a suitably defined notion of asymptotic volume ratio. And out of that, we got an isoperimetric inequality that, very roughly speaking, also shows a constant of integration, okay? That is the value of the boundary, okay? In this case, E has a boundary that's homologous to the boundary of the manifold, okay? It's not just a ball somewhere there, okay? So it's how you get some sort of constant of integration here. Again, only dimension less or equal than 7, substantially because these kind of inequalities are easier, and up to the time we knew how to find it only when sets were smooth. And the mean convex exhaustion was just assumed to exist. Okay, so before you laugh, I want to say that this kind of manifolds are meaningful already in the asymptotically flat situation. Okay, having convex exhaustion is a sort of very strong weakening of asymptotic flatness. Okay, it's like for this kind of problems, all you need of asymptotic flatness is this mean convexity at infinity. Okay, so in place of being asymptotically flatness, you can just assume this exhaustion at infinity in order to get an isoperimetric inequality out of a mean curvature inequality. Okay, so this part of the talk was meant to, okay, to give you this kind of picture and also to motivate what comes next. That is a result that originated in a paper of Gromov. I came in touch recently, that allows you to detect very generally whether a manifold has got a mean convex exhaustion or not. Okay, so this is the last part of the talk, the second part of the talk. Okay. So there is this beautiful theorem that's substantially due to Gromov, okay? 17. It's due to Gromov, but the proof is more or less three lines, okay? 3 lines that I didn't understand. Okay, so so we sort of reworked it, okay? And in the end, concluding that Gromov was sort of completely right, okay? Those 3 lines almost were enough, almost, okay? So this is sort of disappointing because we got a very long proof, and going to understand it better and better, it collapsed in Gromov's proof, okay? There is also a version by Antoine Song, but it's got a very a feature that we were not okay with, that is only for dimension less or equal than 7, while this business started not only for building mean convex exhaustions, but also for another reason I'm not going to discuss today, that is how to extend this picture of geometric inequalities when you have also singularities, okay? But this is a part of the project here I'm not going to discuss now. And, okay, in the version we needed, proved together with Mario Santilli of L'Aquila, in a preprint that I think is going to appear during, at least during this year, maybe in fall. Okay. So no assumptions at all. apart just for simplicity, but it's not needed, one end, okay? So non-compact, one end. The theorem is the following. One of the following holds. At least one of the following holds. One of the following holds. So A, there exists mean convex exhaustion. B. And it's also smooth, okay, but I'm not going to discuss regularity now. B. There exists a mean concave exhaustion. C. There exists a minimal exhaustion, okay? So domains given by minimal hypersurfaces, okay? Minimal exhaustion. Or a pathologic situation. Eh? That none of these hold. The pathologic situation is that there exists a non-compact minimal, not area minimizing, minimal varifold, and it's important here saying varifold, at least my opinion, with finite area. So think in higher codimension, okay? It's like having a non-compact geodesic, okay, with finite length, okay? That it's sort of non-completeness, right? This is a sort of codimension one uncompleteness, okay? Because it could happen that you have a minimal hypersurface that's non-compact, but with finite area, okay? In this case, you don't know how to get exhaustions, okay? Fine, what time is it? Okay. So once you have a theorem like this, what do you do with a theorem like this? You prove that in the setting where you have your mean curvature inequalities, sort of none of these can happen except, for example, mean convexity. Okay. And I'm going to show you in the case that's most simple to understand, that's the one of non-negative Ricci, why the mean curvature inequality, in fact, rules out B, C, and D, leaving you only with A. Okay, so the game becomes excluding B, C, and D. And the very nice thing is that morally, the mean curvature inequalities not only give you the isoperimetric sets, but also rule out B, C, and D. Morally. In the non-negative Ricci curvature, it's very clear. Okay. So example, non-negative Ricci and asymptotic volume ratio that's positive, but you can strongly weaken this assumption. We have that the maximum of 0.8 to the power n minus 1 on any hypersurface DE is greater or equal than C, that's strictly positive and does not depend on E. Okay, it's substantially the Wilmore inequality I wrote here, but in a slightly strengthened form. Okay, that appeared in a very nice paper of Xiaodong Wang, who drastically simplified the proof of the Wilmore type inequality in non-negative Ricci. Okay, so let's see here. We can't have mean concave because otherwise this would be 0 greater than C. For the very same reason, we can't even have minimal because we have 0 greater or equal than a positive C. It's less obvious how to exclude, okay, the pathological thing, okay, but it's not even so surprising, okay, because you can imagine, okay, that this kind of thing, if this was a minimal varifold, okay, with finite area, you still can find something like this, even if it's non-compact, okay. So, and it's not anecdotic, because with the very same proof of Wang, okay, you prove that you get a mysterious positive constant here, okay, also for possible non-compact minimal hypersurfaces with finite area. That is, you don't really need being the boundary of a bounded domain, but having finite area is enough. So for the really and technically it's the very same. So technically it's the very same proof of Wang. Okay, conceptually it's slightly different. Okay, so out of an inequality like this, you exclude B, C, and D. Okay, so out of this theorem, you know that A must hold. And so the very same inequality that gave you the picture of passing from incremental inequality to isoperimetric sets also rule out the bad cases in Gromov's, say, trichotomy, okay? Because this is the pathological thing that you want to exclude from the beginning, okay? Okay, luckily I don't have time to provide the proof of this result, okay? But I think that this is more interesting. What? Yes, but this was my this was my goal at the beginning. Okay, let's try to give you some proof. But before that, one thing that may be confusing is that A, B, and C are not mutually exclusive at all. Usually they happen together. Okay, but you don't mind. You just need that A happens. You don't want that B and C do not happen. In that case, they do not, and it's useful when you can exclude them, because then you have A, okay? But in general, they all happen together, okay? And it's very simple to see that. So, remark, A, B, and C, not mutually exclusive, okay? It's a fascist, you think of something like this, okay? Okay. That again goes something like this, and again, you have minimal hypersurfaces. This is C that keep on happening, okay? You have mean convex ones here. Here you have A, okay? And you also have B. For example, here, okay? Here you have B. And if you keep on repeating this kind of pattern, you get mean convex minimal and mean concave hypersurfaces on and on, okay? It's not the case of negative Ricci. You see, it's sort of, the Ricci curvature is not really negative here, okay? Fine, so a couple of words on Gromov's proof. on the streamlined Gromov's proof. Just one word. The proof by Song not only it doesn't only prove this theorem, it proves much more. Okay, but with a proof that really uses curvature flows, equivariant, min-max theory. That's very strong tools that I don't know how to use in higher dimension, and not even he does. Okay, so this is what we needed in any dimension. Up to dimension 7, there is a stronger result by Song, but up to dimension 7. Okay, it would be nice to have the full picture in all dimensions. By the way, okay, so proof. Very briefly, let K a compact set in M to start from. Okay, K here. I draw a small K. Okay, a small K, and let a very big ball be here. Okay, be 1 over epsilon, say. Okay, and take a function here that we want to see what this function is needed for. Here, p that's smaller or equal than epsilon in a smaller ball here, phi less or equal than epsilon, and here phi is greater or equal than epsilon. Okay, way greater, equal than 1 over epsilon. Okay, so this is a function phi that's almost 0 around k, but we want to let it become 0 far and far in the manifold, but it becomes extremely big outside of a big ball. Okay, why this thing? Because in fact one builds these. In fact, one starts from proving the mean concave case. Through constrained, in this case, this is something that I think it's useful that I didn't understand at the beginning, through constrained minus phi bubbles. Okay, so let E phi constrained minus phi bubble. That is E phi minimizes perimeter of f plus the integral of phi on f among all f that are contained that contain k. Okay. Immediately, if such thing exists and it does not touch k, the mean curvature is minus phi. That's positive. I didn't write it there. That's strictly positive. Phi. Here, the mean curvature would become minus phi, so it's mean concave. Okay. So, very, very briefly, if such a thing, I'm not going to write formulas now. Take that, okay, with this phi. If it exists and it does not touch k, so if phi is somewhere here, so if our phi, so yellow phi, if our phi is somewhere here, we are done. We got a mean concave thing. Okay, we enlarge k, and if this thing keeps on happening, we got the mean concave exhaustion. Okay, but it's not important. Let's stick to one single k. Okay. While for sure it can't become bigger and bigger at infinity because phi is very big outside of b 1 over epsilon. So it will never be useful to minimize that functional there that's got plus the integral of phi. It becomes bigger and bigger if phi wanted to exhaust the manifold. Okay. So the only thing that could go wrong for a single phi, okay, is that it touches k. Okay, it touches k. You don't know anymore the mean curvature on the touching part between phi and k. So the wrong thing is that phi is something like this. Okay. Okay, it touches k. Okay, fine. Then what do? You let phi become 0 on the whole manifold. Okay, so it's becoming 0, still being infinity at infinity. Okay, you lower phi, but letting phi become bigger and bigger at infinity. Okay, you let phi to 0. Okay, so you have now a phi j that goes to 0. This b, okay, this epsilon j goes to 0. Everything becomes a new minimizing sequence. Okay, for a sequence of functionals. Okay, and what could happen? It could happen that you are left with something like this. But if you're left with something like this, now their phi is 0. Okay, so what you get is outward minimizing. But if it's outward minimizing, it's mean convex. Okay, and you are in situation A. Otherwise, you could get that your new E obtained by letting phi j to 0 is like this one. It doesn't touch k, and then it minimizes that with phi equal to 0, and then it's minimal. Or otherwise, and this is the villain of the theorem coming in, okay, it could happen that you have this sort of tails, okay, that in letting phi to 0 becomes thinner and thinner. Keep on doing that, these two things collapse together. In the end, you get a variable, multiplicity two variable, okay, that due to minimization will have finite area, okay, but that's minimal because phi has gone to 0. And this is possibility D appearing. Okay, so this is all of the 4 possibilities appearing. Then there's the smoothing procedure. Okay, but this is completely another thing. Okay, I didn't even started to tell you that. Okay, so I'm out of time. So thank you for the attention.
Questions, comments?
Thanks, Mattia, for giving us another way to prove geometric inequalities. It's amazing. So I was wondering if you can prove higher order geometric inequalities with that. So let's say you start with you suppose that you have a higher Alexandrov-Fenchel inequality and you want to prove Minkowski inequality from there. Is there a way to do that?
Not something similar with Marco many years ago, but problem is that the isoperimetric problem is nice for the direct method. So, for example, at the very beginning, it's easy to get isoperimetric sets in a compact domain. But it's not easy to get minimizers for, say, Minkowski in a compact domain. You don't have the direct method for this kind of functional.
Right.
Or at least we didn't know how to do this kind of thing. So, in general, the algebra would work the very same, I think. But the advantage you get out of the direct method when you're considering the real isoperimetric problem is very different at a first glance. And someone, maybe you would, also sort of convinced me that it couldn't even work this kind of direct method technique. So algebraically, I think it's the very same. But when you use the variational argument, then they no more work in principle.
Not yet? No.
Sorry if I missed it, but what's an example where there's no mean convex exhaustion?
But well, for example, an asymptotically cuspidal manifold.
Okay.
Because all of these things could also have boundary, but okay, but also without boundary. Something like this. We will only have mean concave exhaustions.
Good.
Yeah. Difficult thing is drawing the last the last possibility in the theorem, because you have a metric that to my eyes should look similar to this, okay, but without mean concave exhaustion, where it's cheap for the area to be cheap for the area to be non-compact, okay. It's a sort of tentacle. The situation D, it's a sort of tentacular end with a very tight metric, but I don't know how to draw that.
Okay, any more questions? And if not, let's thank Mattia.
Thank you.